A 50 ohm lossless line connects a signal of 50 kHz to a load of 140 ohms. The load power is 75 microwatt. Calculate the voltage reflection coefficient VSWR, position of Vmax, Imax, V minimum and I minimum. This question is asked several times in end exams. Very important question. Let us see how to answer this type of question. This is a transmission line whose characteristic impedance is 50 ohms. And it is terminated with the load impedance ZR equals to 140 ohms. Then the first case is voltage reflection coefficient tau, which gives the value is, the formula is ZR minus Z0 by ZR plus Z0. If we substitute the values 140 minus 50 by 140 plus 50, which gives 0.4736. And coming to the second bit, VSWR rho equals to 1 plus mod tau by 1 minus mod tau. We substitute these values, 1 plus 0.4736 by 1 minus 0.4736, which gives 2.8. Coming to the third bit, the location of maxima from the load. Location of maxima from the load is given by the formula 2 beta y max minus phi is equals to 2n pi, where n value takes 0, 1, 2, 3 and so on, where this phi gives angle of reflection coefficient. And similarly, for finding the location of minima, the formula is 2 beta y minima minus the phase angle phi is equals to 2n plus 1 times pi. Where n takes the values 0, 1, 2, 3 and so on. For finding the location of first maxima, n value is 0. For finding the location of first maxima, n value is equals to 0, so that 2 beta y maximum minus phi is equals to 0. And we know that the reflection coefficient we have already calculated as 0.4736. This is the magnitude, and the phase angle is 0 degrees, so that the reflection coefficient phase angle is 0 degrees. So 2 beta y max is also equals to 0 here, where phase angle is 0. So from this we can write y maximum is equals to 0. So that means if it is a transmission line terminated with the load impedance ZR, and this is the load at y equals to 0, and this is V maximum. This is V maximum and this is V minimum, and similarly this is V max and this is V minimum. This is second V minima and this is the first V minima. And we already know that the distance between two V max is lambda by 2, and the distance between one V max and one V minima is lambda by 4. From here to here it is lambda by 4, and here the first Y maximum is location of the first maximum is at y equals to 0. So that's why the first V maxima occurs at y equals to 0 at the load itself. So the first maximum of standing wave is located at load itself. Distance between V max and V minima is equals to lambda by 4, and we already know the formula C equals to lambda f and lambda equals to C by f, where C equals to the velocity of the light 3 into 10 power 8 by the frequency is given as 50 into 10 cube, which gives the value 6000 meters. So the lambda value is 6000 meters. Now the location of V minima is equals to lambda by 4 from the load. So lambda is 6000 by 4, which gives 1500 meters. This is from the load. And similarly, from the diagram, here we get the first V maxima, voltage maxima at y equals to 0. Similarly, at y equals to 0, in the opposite of this voltage, we get the current waveform. So this is represented with dotted line, where we get I minima at y equals to 0, and this is I max, this is second I minima, again this is I max. So this is the waveform for current. So the location of I minima is at load y equals to 0, and now the location of I maxima is at lambda by 4 distance. See here, the first I minima is at y equals to 0, and the first I maximum is the distance between I minima and I maxima is lambda by 4 only. So that's why the location of I maxima is at lambda by 4, which gives 6000 by 4, which is equals to 1500 meters. So the calculation of finding the location of V max, V minima, I max and I minima is very important. We are calculating in this way.